Generic data types. We can use generics to create definitions for items like function signatures or structs, which we can then use with many different concrete data types. Let's first look at how to define functions, structs, enums, and methods using generics. Then we'll discuss how generics affect code performance. In function definitions. When defining a function that uses generics, we place the generics in the signature of the function where we would usually specify the data types of the parameters and return value. Doing so makes our code more flexible and provides more functionality to callers of our function while preventing code duplication. Continuing with our largest function, listing 10.4 shows two functions that both find the largest value in a slice. Function largest I32, parameter is a variable list of type slice of a vector of I32s, and it returns an I32. Let mute largest equal list index 0. For reference to item in list.iter, if item is greater than largest, largest equals item. Return largest. Function largest char takes a list which is a reference to a vector of chars, and it returns a char. Let mute largest equal list index 0. For reference to item in list.iter, if item is greater than largest, largest equals item. Return largest. Function main, let number list equal vecbang I32s. Let result equal largest I32 argument reference to number list. Print line, the largest number is result. Let char list equal vecbang of chars. Let result equal largest char of reference to char list. Print line, the largest char is result. Two functions that differ only in their names and the types in their signatures. The largest I32 function is the one we extracted in listing 10.3 that finds the largest I32 in a slice. The largest char function finds the largest char in a slice. The function bodies have the same code, so let's eliminate the duplication by introducing a generic type parameter in a single function. To parameterize the types in the new function we'll define, we need to name the type parameter just as we do for the value parameters to a function. You can use any identifier as a type parameter name, but we'll use T because by convention, parameter names in Rust are short, often just a letter, and Rust's type naming convention is camel case. Short for type, T is the default choice of most Rust programmers. When we use a parameter in the body of the function, we have to declare the parameter name in the signature so the compiler knows what that name means. Similarly, when we use a type parameter name in a function signature, we have to declare the type parameter name before we use it. To define the generic largest function, place type name declarations inside angle brackets between the name of the function and the parameter list, like this. function largest t, list slice vector of t's, return t. We read this definition as the function largest is generic over some type t. This function has one parameter named list, which is a slice of values of type t. The largest function will return a value of the same type t. Listing 10.5 shows the combined largest function definition using the generic data type in its signature. The listing also shows how we can call the function with either a slice of i32 values or char values. Note that this code won't compile yet, but we'll fix it later in this chapter. If we compile this code right now, we'll get this error. Error, binary operation greater than, cannot be applied to type t. Note, an implementation of standard compare partial OR might be missing for t. The note mentions standard compare partial OR, which is a trait. We'll talk about traits in the next section. For now, this error states that the body of largest won't work for all possible types that t could be. Because we want to compare values of type t in the body, we can only use types whose values can be ordered. To enable comparisons, the standard library has the partial OR trait that you can implement on types. You'll learn how to specify that a generic type has a particular trait in the Traits as Parameters section, but let's first explore other ways of using generic type parameters. In struct definitions, we can also define structs to use a generic type parameter in one or more fields using angle brackets syntax. Listing 10.6 shows how to define a generic point struct to hold x and y coordinate values of any type. Struct generic over point of type t, x, t, y, t. In the main function, let integer equal point the fields x5, y10. Let float equal point the fields x1.0 and y4.0. The syntax for using generics in struct definitions is similar to that used in function definitions. First, we declare the name of the type parameter inside angle brackets just after the name of the struct. Then we can use the generic type in the struct definition where we would otherwise specify concrete data types. Note that because we've used only one generic type to define point t, this definition says that the point t struct is generic over some type t, and the fields x and y are both that same type, whatever type that may be. If we create an instance of point t that has values of different types, as in listing 10.7, our code won't compile. Let won't work equal point struct with x5 and y4.0. In this example, when we assign the integer value 5 to x, we let the compiler know that the generic type t will be an integer for this instance of point t. Then, when we specify 4.0 for y, which we've defined to have the same type as x, we'll get a type mismatch error like this. Expected integral variable found floating point variable. To define a point struct where x and y are both generics but could have different types, we can use multiple generic type parameters. For example, in listing 10.8, we can change the definition of point to be generic over types t and u, where x is of type t and y is of type u. So let integer and float equal, right? Okay, so in the struct definition, it says struct point and then in angle brackets t comma u. Now all the instances of point shown are allowed. You can use as many generic type parameters in a definition as you want, but using more than a few makes your code hard to read. When you need lots of generic types in your code, it could indicate that your code needs restructuring into smaller pieces. In enum definitions, as we did with structs, we can define enums to hold generic data types in their variants. Let's take another look at the option t enum that the standard library provides, which we used in chapter 6. Enum option t sum t none. This definition should now make more sense to you. As you can see, option t is an enum that is generic over type t and has two variants: sum, which holds one value of type t, and a none variant that doesn't hold any value. By using the option t enum, we can express the abstract concept of having an optional value. And because option t is generic, we can use this abstraction no matter what the type of the optional value is. Enums can also use multiple generic types as well. The definition of the result enum that we used in chapter 9 is one example. Enum result, generic over types t and e, has variants okay, value t, value e. The result enum is generic over two types, t and e, and has two variants, okay, which holds a value of type t, and which holds a value of type e. This definition makes it convenient to use the result enum anywhere we have an operation that might succeed, that is, return a value of some type t, or fail, that is, return an error of some type e. In fact, this is what we used to open a file in listing 9.3, where t was filled in with the type standard fs file when the file was opened successfully, and e was filled in with the type standard IO error when there were problems opening the file. When you recognize situations in your code with multiple struct or enum definitions that differ only in the types of the values they hold, you can avoid duplication by using generic types instead. In method definitions, we can implement methods on structs and enums, as we did in chapter 5, and use generic types and their definitions too. Listing 10.9 shows the point t struct we defined in listing 10.6 with a method named x implemented on it. So implement over t point t function x taking a mutable reference to self returns reference to t, and the function is reference to self.x. Okay, in main we have let p equal point x5 y10, print line p.x equals p.y. x, and then I guess the value. Listing 10.9, implementing a method named x on the point t struct that will return a reference to the x field of type t. Here we've defined a method named x on point t that returns a reference to the data in the field x. Note that we have to declare t just after impl, so we can use it to specify that we're implementing methods on the type point t. By declaring t as a generic type after impl, Rust can identify that the type in the angle brackets in point is a generic type rather than a concrete type. We could, for example, implement methods only on point f32 instances rather than on point t instances with any generic type. In listing 10.10, we could use the concrete type f32, meaning we don't declare any types after impl. So implement to over point angle brackets f32. The function distance from origin reference to self returns an f32, and it is self.x dot powi2 plus self.y dot powi2 dot squirt. An impl block that only applies to a struct with a particular concrete type for the generic type parameter t. This code means the type point f32 will have a method named distance from origin, and other distances of point t where t is not of type f32 will not have this method defined. The method measures how far our point is from the point at coordinates 0, 0, and uses mathematical operations that are available only for floating point types. Generic type parameters in a struct definition aren't always the same as those you use in that struct's method signatures. For example, listing 10.11 defines the method mixup on the point tu struct from listing 10.8. The method takes another point as a parameter, which might have different types from the self point we're calling mixup on. The method creates a new point instance with the x value from the self point of type t and the y value from the passed-in point of type w. So our struct is generic over struct of point generic struct a struct that's generic over points of type t or u. Oh no, it's a struct. Okay, so yes, right. Okay, I was thinking enum xt yu implement over tu instance or of the struct point tu function mixup vw self and other of type point vw, and it returns point tow. So the point that it returns is x with a value of self.x and y, a value of other.y. In the main function, let p1 equal a point, x is 5 and y is 10.4. Let p2 equal a point, x is hello and y is the char c. Let p3 equal P1 mix up P2. Print line P3.x is P3.x and P3.y is P3.y. In main, we've defined a point that has an I32 for x with a value of 5 and an F64 for y with a value of 10.4. The P2 variable is a point struct that has a string slice for x with value hello and a char for y with value c. Calling mixup on P1 with the argument P2 gives us P3, which will have an I32 for x because x came from P1. The P3 variable will have a char for y because y came from P2. The print line macro call will print P3.x equals 5, P3.y equals c. The purpose of this example is to demonstrate a situation in which some generic parameters are declared with an implementation and some are declared with the method definition. Here the generic parameters t and u are declared after impl because they go with the struct definition. The generic parameters v and w are declared after function mixup because they're only relevant to the method. Performance of code using generics. You might be wondering whether there's a runtime cost when you're using generic type parameters. The good news is, Rust implements generics in such a way that your code doesn't run any slower using generic types than it would with concrete types. Rust accomplishes this by performing monomorphization of the code, that is, using generics at compile time. Monomorphization is the process of turning generic code into specific code by filling in the concrete types that are used when compiled. In this process, the compiler does the opposite of the steps we used to create the generic function in listing 10.5. The compiler looks at all the places where generic code is called and generates code for the concrete types the generic code is called with. Let's look at how this works with an example that uses the standard libraries option t enum. Let integer equal sum5, let float equal sum 5.0. When Rust compiles this code, it performs monomorphization. During that process, the compiler reads the values that have been used in option t instances and identifies two kinds of option t. One is I32 and the other is F64. As such, it expands the generic definition of option t into option I32 and option F64, thereby replacing the generic definition with specific ones. The monomorphized, I said it several times before I messed it up, monomorphized. The monomorphized version of the code looks like the following. The generic option t is replaced with the specific definitions created by the compiler. Enum option I32, sum I32, none. Enum option F64, sum F64, none. Let integer equal option I32, sum 5, let float equal option F64, sum 5.0. Because Rust compiles generic code into code that specifies the type in each instance, we pay no runtime cost for using generics. When the code runs, it performs just as it would if we had duplicated each definition by hand. The process of monomorphization makes Rust's generics extremely efficient at runtime.